These are the answers to the Atomic Structure and Nuclear Chemistry practice test. In the video description area, there is a link to the packet that accompanies this video. So let's begin by taking a look at the first set of questions on this practice test. The instructions say for questions 1 through 5, choose the letter that is correctly associated with one of the people listed above. And they are choice A, John Dalton, choice B, Democritus, choice C, Ernest Rutherford, and choice D, J.J. Thomson. So all 4 of these individuals were studied when you were learning about the development of atomic theory. So in chronological order, let's begin with Democritus. So Democritus was a Greek philosopher, and in Greek, the word atomos means cannot be cut or uncuttable or indivisible, and it's where we get the word atom from. So the correct answer to question 3 is choice B, Democritus. He was a philosopher who believed in the existence of indivisible particles of matter, and the word atomos in his language means uncuttable or indivisible. Now, the next person that was mentioned when you were studying about the development of atomic theory was John Dalton. In 1803, John Dalton published an atomic theory which had 5 major points, and they include all matter is composed of tiny particles called atoms, all atoms of a given element are exactly the same, the atoms of one element have properties that are different from those of any other element, atoms are neither created nor destroyed in any chemical reaction, and atoms of one element combine with atoms of another element to form a compound. A given compound always has the same ratio of elements. Now, the model of the atom in John Dalton's time can be described as the solid sphere model. And in this model, there are no subatomic particles that were known at the time. So there's no nucleus, there's no protons, there's no neutrons, there's no electrons. It's simply like a marble or a hard, solid sphere. So the correct answer to question 2 is choice A, John Dalton. In 1803, John Dalton published an atomic theory in which he stated that all matter is composed of atoms and that atoms of one element can combine with atoms of another element to form a compound. Now, the next person that was mentioned in the history or the development of atomic theory was J.J. Thomson. J.J. Thomson did work with cathode ray tubes. A cathode ray tube is a sealed glass tube that contains a small amount of gas, and when electricity passes through the tube, a beam of light is produced. That beam of light is known as a cathode ray. And Thomson discovered by observing that the cathode ray is attracted toward a positively charged electric plate, that the cathode ray consists of negatively charged particles. These negatively charged particles are electrons. Thomson also discovered that the positively charged material in an atom is much heavier than the negatively charged material in an atom. So Thomson's model of the atom is described as the plum pudding model. In the plum pudding model of the atom, the positive charge has a much greater mass than the negative charge. So the positive charge is the pudding in this model, and the electrons in this model are the raisins in the plum pudding. So the correct answer to questions 1 and 5 in this section of the practice test would be choice D, J.J. Thomson. So in question 1, it says that he did cathode ray tube experiments, which helped him to discover electrons. And then question 5 says his plum pudding model of the atom is based on the fact that the positive material in an atom is much heavier than the negative particles. Now, the last person that I had mentioned in class when you were studying about the development of atomic theory was Ernest Rutherford. Ernest Rutherford did a famous experiment in which a beam of alpha particles was directed at a thin piece of gold foil. Most of the alpha particles passed straight through the gold foil in Ernest Rutherford's experiment. However, there was a very surprising result in which some of the alpha particles were deflected at large angles or bounced backward toward the source. So Rutherford concluded that the atom must contain a tiny, dense center of mass and positive charge, which is the nucleus of the atom. So Rutherford's model of the atom can be described as the nuclear or planetary model. In this model, the atom is mostly empty space, and it has a tiny center called the nucleus, and the rest of the atom would be the electrons in the cloud around the nucleus. So the correct answer to question 4 is C, Ernest Rutherford. In his famous alpha scattering experiment, a stream of alpha particles was directed at a thin piece of gold foil. A small percentage of the alpha particles were deflected at large angles. Now let's take a look at the next set of questions on this practice test. For questions 6 through 10, you have to choose the letter that is correctly associated with one of the atomic models shown above. Now, in this video, I've already mentioned some of the features for the atomic model that's represented by choices A, B, and C, and these atomic models are arranged from left to right, from the earliest model on the left to the most recent model on the right. But since I haven't yet in this video talked about atomic models D and E, let's take a closer look at the details of those two atomic models. So choice D corresponds to a model that is known as the Bohr electron shell model. In this model, you can see a tiny black dot in the center, that is the nucleus, and then you can see several concentric circles around the nucleus. Those circles that get larger and larger, those correspond to a specific orbit in which the electron is traveling around the nucleus in this circular orbit, and it corresponds to different energy levels. So it says in the Bohr electron shell model, electrons occupy specific energy levels. So for example, energy level 1 is that smallest circle in which the electron would be traveling around a particular path that's closer to the nucleus, and then energy level 2 is a little bit larger, and then energy level 3 is even larger. So the electron is traveling in a circular path around the nucleus, and it's only occupying a specific energy level, level 1, level 2, level 3, and so forth. Now the other model, which is a more recent model, a more advanced model, is known as the electron cloud or quantum mechanical model. So the difference between the electron cloud or quantum mechanical model and the Bohr electron shell model is that now the electrons are not traveling in these circular orbits around the nucleus. So what you can see in this model is more of a fuzzy region of space that represents the probable location of the electrons. So instead of the electron traveling in a circular orbit, the word orbital refers to a region in space in which there is a probability of finding the electron. And they have different energy levels as well, but we're looking at a cloud or an orbital and not a defined circular path. So again, the electron cloud or the quantum mechanical model indicates that the electrons are located in these orbitals, which is a region of space in which there is a good probability of finding the electron. Now let's take a look at the models with their names. So from left to right, from earliest to most recent, we have solid sphere model, and that would correspond to choice A. So the correct answer to question 10 is A, the solid sphere model. Then we have the plum pudding model, and that corresponds to choice B. So the correct answer to question 9 is choice B, the plum pudding model. Then we have the Rutherford nuclear or planetary model of the atom, and that would correspond to choice C. So the correct answer to question 8 is choice C, the nuclear or planetary model. And then the Bohr electron shell model represents choice D. So the correct answer to question 6 is choice D, the Bohr electron shell model. And finally, choice E, the electron cloud or quantum mechanical model, that would correspond to choice E, and that is the answer to question 7. So the answers to questions 6 through 10 are D, E, C, B, and A. Now let's take a look at the next section of the practice test. It says, for the sentences numbered 11 through 17, fill in each blank with one of the following words: protons, electrons, or neutrons. Number 11 says a neutral atom of lithium-7 contains an equal number of blank and blank. If we look on the periodic table and we can find the symbol for the element lithium, which is Li, we can see that lithium has an atomic number of 3, which means that lithium contains 3 protons in its nucleus. There is the symbol for lithium-7, and the mass number is the sum of the protons and neutrons added together. So lithium has 3 protons and 4 neutrons because 3 plus 4 is 7. This is a neutral atom of lithium, so therefore it is not an ion, and it has the same number of electrons as protons. So the number of protons, the number of electrons are the same, so the answer to number 11 is protons and electrons. Now let's take a look at number 12. In number 12, it says, when an atom of oxygen gains 2 blank, it becomes an oxygen anion. So here's a little information about positive and negative ions. An ion is an atom that has an overall charge because it does not have the same number of protons and electrons. When an ion has a positive charge, it is known as a cation. When an ion has a negative charge, it is known as an anion. An atom will become a cation when it loses electrons, and an atom will become an anion when it gains electrons. And that's what happened in question 12. When an atom of oxygen gains 2 electrons, it becomes an oxygen anion, which has a negative charge. Now let's take a look at number 13. It says the nucleus of a neutral atom of boron-10 contains 5 blank and 5 blank. On the periodic table, we can find the elemental symbol for boron, which is capital B, and we can see that boron has an atomic number of 5, which means it has 5 protons. Because the mass number is the sum of the protons and neutrons, and it has a mass number of 10, that means it has 5 neutrons, because 5 protons plus 5 neutrons would equal a mass number of 10. Since this is a neutral atom of boron and not an ion, then the number of electrons are the same as the number of protons. So now, since we have 5 protons, 5 neutrons, and 5 electrons, to answer number 13, we have to consider where are these particles located in the atom. And the first part of number 13 said the nucleus of a neutral atom of boron-10. So the electrons are located outside the nucleus of the atom, but the protons and the neutrons are located in the nucleus. So the correct answer to number 13 is 5 protons and 5 neutrons, which are located in the nucleus of the atom. Now, moving on to number 14. It says, a neutral atom of carbon-14 contains 2 more blank than a neutral atom of carbon-12. On the periodic table, we can see that carbon has an atomic number of 6. This means that carbon has 6 protons. And so to consider a neutral atom of carbon-12, that would be 6 protons, 6 neutrons, and 6 electrons. Remember that the mass number is the sum of the protons and neutrons added together. So for carbon-14, the reason why carbon-14 has a mass number that's heavier than that of carbon-12 is that carbon-14 has 2 extra neutrons. Carbon-14 has 6 protons, 8 neutrons, and 6 electrons. So the correct answer to number 14 is that carbon-14 contains 2 more neutrons than carbon-12. And now in number 15, it says, a neutral atom of cobalt-60 contains the same number of blank as the cobalt-59 ion that carries a charge of +2 or 2+. Let's go ahead and consider the number of protons, neutrons, and electrons for each of these particles. On the periodic table, we can see that the element cobalt, which has the symbol capital C, lowercase o, has an atomic number of 27. So that means that cobalt has 27 protons. A neutral atom of cobalt-60 has 27 protons. It has 33 neutrons because 27 plus 33 equals the mass number of 60. And since this is a neutral atom, then the number of electrons is the same as the number of protons, so it would have 27 electrons. Now for the ion, it has a mass number of 59. So it has 27 protons because it still has the same elemental identity. This is still cobalt, so 27 protons. 27 plus 32 equals 59, so it has 32 neutrons. And then when an atom loses electrons, it becomes a cation, which is positively charged. So therefore, the atom lost 2 electrons to carry a charge of +2. So this particle only has 25 electrons. Now, as we can see, the number of protons, neutrons, and electrons for each of these particles, the only thing that they have in common that's exactly the same is the number of protons. And so that is the answer to number 15. A neutral atom of cobalt-60 contains the same number of protons as the cobalt-59 ion that carries a +2 charge. Now let's look at number 16, which says, a neutral atom of magnesium-25 contains the same number of blank as a neutral atom of silicon-27. Looking on the periodic table, we can see that the atomic number of magnesium is 12, and the atomic number of silicon is 14. So we have a neutral atom of magnesium-25, and we have a neutral atom of silicon-27. Let's consider the number of protons, neutrons, and electrons for each of these particles. Magnesium has 12 protons, and since protons plus neutrons equals the mass number, 12 plus 13 equals 25. So magnesium-25 has 13 neutrons, and since it is neutral and not an ion, its number of electrons is the same as its number of protons. So 12 protons, 13 neutrons, and 12 electrons. Now for silicon-27, it would be 14 protons, 13 neutrons, because 14 plus 13 equals 27. Protons plus neutrons equals the mass number. And again, this is a neutral atom, so the protons and electrons are the same, 14 protons and 14 electrons. Now we can see side by side that magnesium-25 and silicon-27 have the same number of neutrons. So that is the answer to question 16. They have the same number of neutrons. Now let's look at number 17. it says that the sodium ion with a mass of 23 and a charge of positive 1 contains the same number of blank as the oxygen ion, which has a mass number of 16 and a charge of negative 2. Let's start with the atomic number of each element. So for sodium, the atomic number of sodium is 11, and for oxygen, the atomic number of oxygen is 8. Here are the symbols for each of these ions. Sodium has a mass number of 23 and a charge of positive 1. Oxygen has a mass of 16 and a charge of negative 2. So we know that sodium has 11 protons, and since the protons plus the neutrons equals the mass number, 11 plus 12 is 23. That's 11 protons and 12 neutrons. When an atom loses electrons, it becomes positively charged. So since sodium has a charge of plus 1, that means that the sodium atom lost 1 electron. So this ion has 10 electrons instead of 11. Now for the oxygen, 8 protons because of the atomic number of oxygen. It has a mass of 16, so 8 protons plus 8 neutrons gives us the mass number of 16. And when an atom gains electrons to become negatively charged, that means that the oxygen must have gained 2 electrons to carry a negative 2 charge. So now we can see side by side that they have a different number of protons, they have a different number of neutrons, but these two ions have the same number of electrons. They each have 10 electrons, and so that is the answer to number 17. Now let's move on to our next question in this practice test. This is question 18. It says, which of the following statements concerning a cathode ray is true? Now, when J.J. Thomson was investigating the properties of cathode rays, Thomson discovered that a cathode ray is attracted toward a positively charged plate. Therefore, a cathode ray is composed of negatively charged particles. So, since a cathode ray is attracted toward a positively charged plate, we know that choice A in question 18 is not true. Choice A says a cathode ray is attracted toward a negatively charged plate, but in fact, a cathode ray is attracted toward a positively charged plate. So we can eliminate choice A. In choice B, it says the path of a cathode ray cannot be affected by a magnetic field. Take a look at the following video, which shows how a magnet affects a cathode ray.
The cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet.
So because the path of a cathode ray is affected by a magnetic field, we can eliminate choice B. Now take a look at choice D. It says, in a famous experiment, cathode rays were directed at a thin piece of gold foil, and some of them were scattered at large angles. Choice D is incorrect. It wasn't cathode rays, but rather a beam of alpha particles that was directed at a thin piece of gold foil in Ernest Rutherford's famous gold foil experiment. So not cathode rays, but a beam of alpha particles. So we can eliminate choice D. And now moving on to why choice C is the correct answer. In the plum pudding model of the atom, it was because the positive charge was much heavier than the negative charge that we have positive charge as the pudding and the tiny electrons as the raisins. So the positive charge is much heavier than the negative charge particles. So a cathode ray, which is composed of electrons, is composed of tiny particles whose mass is much less than the mass of protons. So that is the correct answer to question 18. Now let's take a look at our next question. This is question 19. It says, in which of the following are the number of protons the same as the number of electrons? Let's start with choice A. We have an ion of lithium, which has a mass number of 6 and has a charge of positive 1. Now, the atomic number of lithium is 3, so it has 3 protons. This particle has a mass number of 6, so the sum of the protons and neutrons equal the mass number, so 3 protons and 3 neutrons. And then because it has a charge of positive 1, that means that this atom must have lost 1 electron to form an ion with a positive 1 charge. So it has 2 electrons. Moving on to choice B, helium has atomic number 2. This particle has a mass number of 4 and has a charge of positive 2. So it has 2 protons, 2 neutrons, because protons plus neutrons equal the mass number. And when an ion has a positive 2 charge, that means that the atom must have lost 2 electrons. So this particle has 0 electrons. Moving on to choice C, oxygen has atomic number 8. This particle has a mass number of 16 and has a charge of negative 2. So 8 protons because the atomic number is 8, 8 neutrons because the sum of the protons and neutrons added together, 8 plus 8, equals the mass number of 16. And when an atom gains 2 electrons, it will have a charge of negative 2, so this particle has 10 electrons. Now we come to choice D. It's the only one of these 4 choices that is a neutral atom as opposed to a positive or a negative ion. So this particle of fluorine is a neutral atom. It has 9 protons. It has 10 neutrons because the sum of the protons and the neutrons equals the mass number of 19. But because it's neutral, the protons and the electrons are the same for this neutral atom. So 9 protons and 9 electrons, that makes choice D the correct answer to question 19. Now let's take a look at question 20. It says, in which of the following are the number of protons the same as the number of neutrons? Let's start with choice A. We have potassium 40. The symbol for potassium is capital K. Potassium has atomic number 19, so it has 19 protons. And since the mass number is equal to the sum of the protons and the neutrons, that means that potassium 40 has 19 protons and 21 neutrons, because 19 plus 21 equals 40. In choice B, we have carbon. Carbon has atomic number 6. This is an isotope of carbon 14. So we have 6 protons and 8 neutrons because 6 plus 8 equals 14. In choice C, we have an atom of sulfur 32. Sulfur has atomic number 16. So this atom of sulfur 32 has 16 protons and 16 neutrons because 16 plus 16 equals 32 for the mass number. And then in choice D, this is an atom of germanium, which has a mass number of 66. 32 protons plus 34 neutrons gives us a mass number of 66. So looking at these 4 choices, the only one that has the same number of protons and neutrons is choice C. Sulfur 32 has 16 protons and 16 neutrons. So that makes choice C the correct answer to question 20. Now let's take a look at question 21, which says, in which of the following are the number of electrons the same as the number of neutrons? Let's start with choice A. In choice A, we have an ion of beryllium. It has a mass number of 9, and it has a charge of positive 1. Since the atomic number of beryllium is 4, that means that this particle has 4 protons. Because the mass number is the sum of the protons and the neutrons added together, and 4 plus 5 equals 9, this particle has 5 neutrons. If an atom loses 1 electron, it becomes a positive ion with a +1 charge. And that's what happened. So we have 4 protons, but only 3 electrons, and that would give this particle a positive 1 charge. So 4 protons, 5 neutrons, and 3 electrons. Now moving on to choice B, this is oxygen, which has atomic number 8. This particle has a mass number of 18, and it has a charge of -2. So atomic number 8 means 8 protons. The sum of the protons and the neutrons gives us a mass number of 18, so 8 protons and 10 neutrons. 8 plus 10 is 18. And when an atom gains 2 electrons, it will have a charge of -2. So this particle has 10 electrons, 8 protons, 10 neutrons, 10 electrons. Moving on to choice C, silicon has atomic number 14. This particle has a mass number of 28, and it has a charge of +4. So atomic number 14, 14 protons, mass number of 28, protons plus neutrons equals mass number, so 14 protons, 14 neutrons. But if an atom loses 4 electrons, it will have a +4 charge to become an ion. So this has only 10 electrons, 14 protons, 14 neutrons, and 10 electrons. Finally, choice D, it's a neutral atom of chlorine 35. The atomic number of chlorine is 17. 17 protons, 18 neutrons, because 17 plus 18 equals 35. And then because this is a neutral atom, the number of protons and electrons are the same, so 17 protons and 17 electrons. Now, again, question 21 said, in which of the following are the number of electrons the same as the number of neutrons? So the correct answer is choice B. This ion of oxygen 18 with a -2 charge has 10 neutrons and 10 electrons. So correct answer to 21 is choice B. Now let's take a look at our next question. This is question 22. It says, which of the following isotopes of strontium, Sr, should have the highest natural abundance? And our 4 choices are strontium 86, strontium 87, strontium 88, and strontium 89. On the periodic table, we can see that the average atomic mass of strontium is 87.62. Therefore, the isotope of strontium with the highest natural abundance should be strontium 88, because the mass number 88 is closer to 87.62, or the average atomic mass, than any of the other isotopes. And I verified this information by looking up the information about the isotopes of strontium, and I discovered that it is, in fact, strontium 88 that has the highest value for its natural abundance. So the correct answer for question 22 is strontium 88. Again, that mass number, 88, is closer to the average atomic mass of 87.62 than any of the other isotopes listed. Now let's take a look at our next question. This is question 23. It says, chlorine exists naturally with 2 stable isotopes, chlorine 35 and chlorine 37. Which of the following is most likely to represent the natural abundance of these 2 isotopes of chlorine? When we look on the periodic table, we can see that the average atomic mass of chlorine is 35.45. So based on this information, and the fact that we have two different stable isotopes of chlorine with mass numbers of 35 and 37, we can predict that the isotope with the higher natural abundance should be chlorine-35, because the mass number 35 is closer to the average atomic mass of 35.45 than the mass number 37 is. So therefore, we would predict that the natural abundance of chlorine-35 should be greater than 50%. So based on that information, we can eliminate choice D, which shows a natural abundance of chlorine-35 of only 36%. Now, to decide whether the correct answer to question 23 is choice A, choice B, or choice C, we have to do the math, which involves multiplying the mass number of each isotope times its percent abundance as a decimal, and then adding those two values together. So starting with choice A, it would be 35 times 0.86 plus 37 times 0.14. And we get a value of 35.28 for that calculation. I'll repeat that process for choices B and C. And so now we can see our calculated values for the average atomic mass based on the information in choices A, B, and C. So the correct answer for question 23 is choice B, because when we do that math of 35 times 0.76 plus 37 times 0.24, we get a value of approximately 35.5, and that is the closest to the average atomic mass of chlorine as reported on the periodic table. So the correct answer to question 23 is choice B, which shows chlorine-35 with an abundance of 76% and chlorine-37 with a percent abundance of 24%. Now let's take a look at our next question. This is question 24. It says, which of the following statements is true concerning aluminum-28? In choice A, it says aluminum-28 has a higher natural abundance than aluminum-27. To verify if this statement is true or false, let's take a look at the average atomic mass of aluminum on the periodic table. So here we can see that the average atomic mass of aluminum is 26.98. So if I have to choose between aluminum-27 and aluminum-28, I would predict that the isotope with the higher natural abundance should be aluminum-27, because the mass number of 27 is closer to the average atomic mass of 26.98 than the mass number of 28 is. So therefore, I would disagree with the statement in choice A. Aluminum-28 should not have a higher natural abundance than aluminum-27. Moving on to choice B, it says aluminum-28 has one more proton than aluminum-27. I would disagree with that statement, because if these are two different isotopes of the same element, then they have to have the same number of protons. So aluminum-28 has 13 protons because of atomic number 13, and so does aluminum-27. So the correct answer to question 24 is either C or D, and both of these statements involve beta decay. Let's take a closer look at the details of beta decay. When you were studying nuclear chemistry, you learned that in beta decay, the mass number of the radioisotope is unchanged, and the atomic number increases by 1 unit. For example, if carbon-14 undergoes beta decay, it gives off a beta particle, and then the new isotope is now nitrogen-14, where the atomic number of carbon, which was 6, changes to an atomic number of 7, and that becomes nitrogen. So let's go back and take a look at aluminum-28 undergoing beta decay. So when aluminum-28 undergoes beta decay, the other particle that would be produced would have a mass number of 28, but now has an atomic number of not 13, but rather 14. So what element on the periodic table has atomic number 14? And that would be silicon, which has the symbol Si. So when aluminum 28 undergoes beta decay, it produces silicon 28. So the correct answer to question 24 is choice D. When aluminum 28 undergoes beta decay, silicon 28 is produced. Now let's take a look at our next question. This is question 25. In part A, it says, the data in the table above represents the natural abundance of two stable isotopes of a certain element. Use this information to calculate the average atomic mass of the element. So the math involved in this calculation is to take the mass number of each isotope and multiply by the natural abundance expressed as a decimal, and then add these two values together. So the calculation involves 107 times 0.518 plus 109 times 0.482. And when we do that calculation, we get an answer for the average atomic mass of 107.964. Now, moving on to part B, it says to write the symbol for the element whose average atomic mass is most similar to the value that you calculated in part A. And so looking on the periodic table, we can see that the elemental symbol should be Ag. That's the elemental symbol for the element silver. And silver has an average atomic mass of 107.87, which is very similar to the answer that was calculated in part A. Let's move on to our next question. This is question 26. It says the element antimony, which has the elemental symbol Sb, exists naturally as two different isotopes, antimony 121 and antimony 123. Use this information and the average atomic mass of antimony, which when we look on the periodic table, the average atomic mass of antimony is 121.76. So use this information to calculate the natural abundance of each isotope of antimony. If we were to set up the calculation, we would multiply the mass number of each isotope by the value for the percent abundance expressed as a decimal. But since we don't know what these values are, let's take a look at the relationship between these unknown values. So for example, if the natural abundance of antimony 121 were 10%, then the natural abundance of antimony 123 would be 90%, and expressed as a decimal, that would be 0.1 and 0.9. Of course, we don't know what these values are, so for example, it could be 20% and 80%, and we would use the values 0.2 and 0.8, or perhaps if it was 30% and 70%, or perhaps 40% and 60%. So since we don't know what these values are, but we do know that we should express them in this calculation as decimal values that are less than 1, we can use an algebraic method of solving for these unknown quantities. So what we can do is let x, an unknown variable, represent the numerical value for the percent abundance of antimony 121. And that would be in the form of a number that is less than 1. But as you can see, the 2% abundance values would add together to equal the number 1 when these values are expressed as a decimal. So 1 minus x, that quantity would represent the numerical value for the percent abundance of the other isotope, antimony 123. So no matter what these values are, x could represent the percent abundance of antimony 121, and then 1 minus x would represent the percent abundance for antimony 123. Again, we set these equal to the average atomic mass of the element antimony as reported on the periodic table. So now let's do the algebra. We have 121 times x, and then we have 123 times the quantity 1 minus x. So we have 121x plus 123 minus 123x equals 121.76. When we combine the x terms on the left side of the equation, we get negative 2x. And if we subtract the number 123 from both sides of the equation, 121.76 minus 123, we get negative 1.24. If we divide both sides of this equation by the number negative 2, we can solve for x. And so x is equal to 0.62 when we do that calculation. So if x represents the number 0.62, then 1 minus x, or 1 minus 0.62, would give us a value of 0.38. So those numbers would represent the percent abundance, the natural abundance of each isotope. So the answer to question 26, based on this algebra, is the following. The natural abundance of antimony 121 would be 62%, and the natural abundance of antimony 123 would be 38%, based on this method of using algebra to solve for the natural abundance of each isotope. So that is the answer to question 26. Let's move on to our next question. This is question 27. It says, fill in the missing information in the table below. Each element symbol must include the mass number and the charge on the ion if there is a charge. So we have element symbol, mass number, protons, electrons, and neutrons. So I'll start with this particular column, which is the mass number. For the first 3 rows of this table, the mass number is listed in the upper left corner of that element symbol. So for the first symbol, that would be a mass number of 231. For the next symbol, the mass number is 79. And for the next symbol, the mass number is 137. Now, moving on to the final 3 rows of this table, in order to determine the mass number, we have to add the protons and the neutrons together. So for 15 protons plus 17 neutrons, 15 plus 17, that gives us a mass number of 32. And then for the next row, that would be 45 protons plus 58 neutrons. 45 plus 58 is 103. And for the final row of the table, that would be 55 protons, 78 neutrons. So 55 plus 78 is 133. Now let's move on to the next column in this table, which is protons. We have to go find the element symbol on the periodic table and determine the atomic number of that element to figure out the number of protons. So for the element symbol Pa, which is protactinium, the atomic number is 91. That means that protactinium has 91 protons. For our next elemental symbol, which is Se, that is the element selenium. Selenium has atomic number 34, which means it has 34 protons. And our next symbol, which is Ba, that's the element barium. Barium has atomic number 56, so it has 56 protons. Now let's move over to the far column in this table, which is the number of neutrons. If the mass number is the sum of the protons and the neutrons added together, but if we already know the mass number and the number of protons, then we can subtract those 2 values. So mass number minus number of protons will give us the number of neutrons. So for the first row of that table, that would be a mass number of 231 minus 91 protons. So 231 minus 91 gives us a value of 140 neutrons. In the next row of the table, we have a mass number of 79. We have 34 protons, so 79 minus 34 will give us a value of 45 neutrons. In the next row of the table, we have a mass number of 137. If we subtract 56, the number of protons, 137 minus 56, we get 81 neutrons. Moving on to the next row of the table, it has a mass number of 157. If we subtract the number of protons, 157 minus 64 gives us a value of 93 neutrons. In the next row of the table, we have a mass number of 89. If we subtract the number of protons, 89 minus 39 gives us a value of 50 neutrons. And then a mass number of 80. We subtract 35 protons, 80 minus 35 gives us a value of 45 neutrons. Now I'd like to move over to the column for electrons. To figure out the number of electrons, we have to consider whether or not this symbol has a charge. Is this a neutral atom, or is it a charge of either positive or negative? So our first element symbol, there is no charge listed. This is a neutral atom, so the number of protons is the same as the number of electrons, which means if we have 91 protons, we also have 91 electrons. But our next symbol is an ion, and the charge on this ion is -2. So when an atom gains 2 electrons, it will have a charge of -2. So this particular substance, it has 34 protons, but the number of electrons will be greater than the number of protons. So the answer is 36. If it gained 2 electrons, it would have 36 electrons and a charge of -2. In our next symbol, we have a charge of +2. If an atom loses 2 electrons, it would have a charge of +2. So barium has 56 protons, but this ion only has 54 electrons. So the number of electrons is less than the number of protons. Now let's move on to the first column, which is the element symbol. We have to go find the element symbol on the periodic table based on the atomic number, which is the number of protons. So 64 protons. Let's go look for an element that has atomic number 64, and that happens to be the elemental symbol Gd, which is the element gadolinium. So gadolinium has a mass number of 157 in this table. Now we don't have to write that number in the bottom left corner, but we do have to write the mass number. So you could write it like this, with the elemental symbol Gd and then the mass number of 157. It's okay if the mass number that we are given in this table does not match the exact average atomic mass of the element. So we go with the mass number, not the average atomic mass. Since this particular element is listed with 64 protons and 64 electrons, that means it is a neutral atom and there is no charge. In our next example, in the next row of the table, we have 39 protons. Let's go look for the element that has atomic number 39. This would be the element that has the symbol capital Y. This is the element yttrium. So the mass number that's listed here in the table is 89. But unlike the previous example, which was a neutral atom, this is going to be an ion because the number of electrons is not the same as the number of protons. So what happened here is that the atom must have lost 3 electrons to go from 39 to 36. And when an atom loses electrons, it becomes positively charged. So because the atom lost 3 electrons, it will have a charge of +3. And you can write the symbol for the charge as either +3 or 3+. They mean the same thing. Moving on to our next elemental symbol, we're looking for atomic number 35. So atomic number 35 is capital B, lowercase r. That's the elemental symbol for bromine. So bromine is Br, and this mass number happens to be 80, as listed in the table. And with respect to the charge, we do have a different number of protons and electrons. We have 35 protons and 36 electrons. So that means that the atom must have gained one electron. When an atom gains an electron, it becomes negatively charged with a charge of -1. And you can just write the charge as minus. It's understood that when you write that minus sign, that would mean -1 charge. Moving on to the next row of this table, I can see 15 protons. So we're looking for the element symbol for atomic number 15 on the periodic table, and that would be the element phosphorus, which has the elemental symbol capital P. Notice that the mass number as listed in this table is actually 32, and that doesn't match the average atomic mass of phosphorus on the periodic table, which is 30.97. So in this table, we have to go with the mass number, which may not necessarily be the same as the average atomic mass. So I have phosphorus, 32. Now let's take a look at the electrons. We have 15 protons and 18 electrons. So that means that the atom must have gained 3 electrons. And when an atom gains 3 electrons, it now has a charge of -3. So we can write either -3 or 3- for the charge on this ion. Moving on to the next row of the table, we have 45 protons. So looking for an element with atomic number 45, and that would be the element rhodium, which has the symbol RH. We have a mass number of 103. And as far as the electrons are concerned, the electrons in this symbol are the same as the number of protons. So 45 protons, 45 electrons, that means that this would be a neutral atom, and there is no charge. It is a neutral atom and not an ion. And now for the symbol of the final row of this table, it's going to be 55 protons. So atomic number 55, that is the element cesium, which has the symbol CS. The mass number listed in this table is 133. So we have cesium with a mass number of 133. Now let's take a look at the electrons. We have 55 protons, but only 54 electrons. So when an atom loses 1 electron, it now becomes an ion with a +1 charge. So we can write either +1 or simply the plus symbol to represent a +1 charge. So let's take a look. This is now the answer to all of the missing information in the table for question 27. Now let's take a look at our next question. This is question 28. It says, write balanced nuclear decay equations for each of the following. In part A, it says radon-222 undergoes alpha decay. And in part B, it says chromium-55 undergoes beta decay. When you were learning about nuclear chemistry, you learned about alpha and beta decay. Here's an example of alpha decay for uranium-238. In alpha decay, the mass number of the unstable isotope decreases by 4 units, and the atomic number decreases by 2 units. So if I start with uranium-238, which has atomic number 92, and that isotope gives off an alpha particle, which has the symbol 4/2, and there's that alpha symbol, the mass number decreases from 238 to 234, and the atomic number decreases from 92 to 90, and the element thorium, Th, has atomic number 90. So now here in part A, we have radon-222. Let's go find the symbol for radon on the periodic table so we can find the atomic number. So the atomic number of radon is 86. So the symbol for radon-222 has a mass number of 222 and the atomic number is 86. It gives off an alpha particle, so there's the alpha symbol with 4/2. And so now 222 minus 4 gives us a mass number of 218, and 86 minus 2 gives us an atomic number of 84. Now let's look on the periodic table and find what element has atomic number 84. And that turns out to be the element polonium, which has the symbol capital P lowercase o. So the answer to part A of question 28 is that radon-222 undergoes alpha decay to produce a particle of polonium-218. Now, moving on to part B, chromium-55 undergoes beta decay. When you were studying beta decay, here's an example of beta decay for carbon-14, you learned that the mass number of the isotope is unchanged, and the atomic number actually increases by 1 unit. So when carbon-14 undergoes beta decay, it gives off a beta particle, which has that beta symbol and the number 0 over -1. The new particle still has the same mass number of 14, but now it has atomic number 7 instead of 6. So carbon-14 gives off a beta particle to produce nitrogen-14. So here in our example, we have chromium-55 undergoes beta decay. Let's find the atomic number of chromium on the periodic table. The atomic number of chromium is 24. So chromium with a mass number of 55, the atomic number is 24, undergoes beta decay, gives off the beta particle. So there's the beta symbol with the 0 over -1. And now the new particle that is produced will have a mass number of 55, but the atomic number is now 25. So it increases the atomic number by 1 unit. Let's look on the periodic table to see what element has atomic number 25. And that turns out to be the elemental symbol Mn. That's the element manganese. So when chromium-55 undergoes beta decay, it produces a beta particle, and it also produces manganese-55. So there are the answers to question 28. Now let's take a look at our next question. This is question 29. All of the remaining questions in this practice test have to do with the concept of half-life. In question 29, it says the half-life of radium-233 is 30 seconds. A chemist has a sample of radium-233 that has an initial mass of 40 milligrams. Now, if one half-life period occurs for this sample, that would take a period of 30 seconds, and the mass of our radium-233 would decrease from 40 milligrams to 20 milligrams. If that decay process continues, then after another half-life period, in other words, after another 30 seconds, the mass of our radium-233 would decrease from 20 milligrams to 10 milligrams, again, decreasing by half. So this question says, calculate how many milligrams of radium-233 will be present in the sample after a period of 90 seconds. So if we take the total time period for the nuclear decay process to occur, and we divide by one half-life period, then we can figure out the number of half-life periods. And the number of half-life periods would be the number of times that the mass of the sample decreases by half. So in this case, we have 90 seconds. Each half-life is 30 seconds. So that's going to be a total of 3 half-life periods. So right now we have 10 milligrams, but if another 30-second half-life period occurs, then the mass of our sample will decrease from 10 milligrams to 5 milligrams. So we started with 40 milligrams of this sample, and we have 3 half-life periods. So the mass of our sample has decreased from 40 to 20, from 20 to 10, and then finally from 10 to 5 milligrams. So the answer to question 29 is the number of milligrams of radium-233 that will be present in the sample after a period of 90 seconds? The answer is 5 milligrams. Now let's take a look at our next question. This is question 30. It says the half-life of sodium-24 is 15 hours. A chemist has a sample of sodium-24 that has already experienced the process of nuclear decay, and the final mass of sodium-24 in the sample is equal to 1.80 milligrams. Now, if we were to go backwards in time and imagine how much of this sodium-24 was present in the sample, then 15 hours ago, there would have been twice as much as there is now. And so 1.80 milligrams times 2 gives us a value of 3.60 milligrams. And we can keep proceeding backwards in time. So another half-life period would be another 15 hours. And 3.60 milligrams times 2, that means that earlier there would have been 7.20 milligrams. And we can keep going backwards in time. So another 15 hours would have occurred. That would mean that the original sample would be twice as much as it is now. So 7.2 times 2 is 14.4. So remember that the total time divided by the half-life is equal to the number of half-life periods. So what's the total time in this problem? It says calculate the mass of sodium-24 in units of milligrams that was originally present in the sample 60 hours ago. So the total time is 60 hours. One half-life period is 15 hours. And because 60 divided by 15 is equal to 4, that means that there are a total of 4 half-life periods. I'm going to add one more half-life period. So going backwards in time one more time, 14.4 milligrams times 2 gives us a value of 28.8 milligrams. So what you can see from left to right would be that we have 28.8 milligrams of this radioactive sodium-24, and then every 15 hours, the mass of our sample has decreased by half. So 28.8 divided by 2 is 14.4. 14.4 divided by 2 is 7.2. 7.2 divided by 2 is 3.6. And then finally, half of 3.6 is 1.80. But since the question is asking us to calculate how many milligrams of sodium-24 was originally present in the sample 60 hours ago, that would be 4 half-life periods. The correct answer to question 30 is 28.8 milligrams. And we determined this by moving backwards in time, considering that we had a total of 4 half-life periods. So again, the correct answer to question 30 is 28.8 milligrams. Now let's take a look at our next question. This is question 31. It says the half-life of fermium-253 is 3 days. A chemist has a sample of fermium-253 that has an initial mass of 240 milligrams. So if the half-life is 3 days, that means that every 3 days, the mass of this sample will decrease by half of its original value. So half of 240 is 120. So after a 3-day period, we would have 120 milligrams of this fermium-253 sample. And after another 3 days, the mass of our sample would decrease from 120 milligrams to 60 milligrams. And after another 3-day period, the mass of our sample would decrease from 60 milligrams to 30 milligrams. And so if we read the information in question 31, it says, calculate the total time in days that is required for the mass of fermium-253 to decrease to a final value of 7.5 milligrams. So right now, looking at the information on this slide, I'm at 30 milligrams. So after another 3 days, another half-life period, 30 milligrams would decrease to a value of 15 milligrams. And then whenever 15 milligrams decays further, that'd be another 3-day period. 15 divided by 2 is 7.5 milligrams. And so that is our final value. So let's consider how many half-life periods was required to get from 240 milligrams to 7.5 milligrams. Well, I can see 1, 2, 3, 4, 5 half-life periods. And each half-life period is 3 days. So the total time would be 3 days times 5. That's a total of 15 days. So we started with 240 milligrams, and then dividing by 2, that's 120 milligrams. Dividing by 2, that's 60 milligrams. Dividing by 2, that's 30 milligrams. Dividing by 2, that's 15 milligrams. And then finally, dividing by 2, that's 7.5 milligrams. And that's 1, 2, 3, 4, 5 half-life periods. 5 half-life periods times 3 days. The answer to question 31, the total time that is required for the mass of this fermium-253 to decrease from 240 milligrams to a final value of 7.5 milligrams, the answer to question 31 is 15 days. Now let's take a look at our next question. This is question 32. It says, a sample of fluorine-18 undergoes nuclear decay, and the mass of fluorine-18 in the sample changes from an initial mass of 51.2 milligrams to a final mass of 0.800 milligrams over a total time period of 660 minutes. Now, what I'm going to do is determine how many half-life periods have occurred during the total process of nuclear decay. So 51.2 divided by 2 would give me a value of 25.6 milligrams. So that would be 1 half-life period. 25.6 divided by 2 gives me a value of 12.8 milligrams. I'm going to keep going until I get to a final mass of 0.800 milligrams. So 12.8 divided by 2 is equal to 6.4. 6.4 divided by 2 is equal to 3.2. 3.2 divided by 2 is equal to 1.6. And now one more half-life period is all I need. 1.6 divided by 2 is 0.8 milligrams. So looking from the beginning to the end, from left to right on this slide, I can see that I started with 51.2 milligrams, and then after 1, 2, 3, 4, 5, 6 half-life periods, I have now reached a final mass of 0.8 milligrams of this radioactive fluorine-18 isotope. So in this question, it says that the total time period for this nuclear decay is 660 minutes, and we have to calculate the half-life of fluorine-18 in units of minutes. So 660 minutes divided by 6 half-life periods, 660 divided by 6, that gives me what 1 half-life period would be worth, and the answer is 110 minutes. So according to the information in this question, we started with 51.2 milligrams, and then after a total of 6 half-life periods, we have a final mass of 0.8 milligrams. Again, that's 660 minutes divided by 6 half-life periods. And so the correct answer to question 32, what is the half-life of fluorine-18? It's 110 minutes. Now, this is the answer to question 32, which happens to be the last question on this practice test. So this is the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching, and good luck studying for your test on atomic structure and nuclear chemistry.